AI is now widely used in medical applications, for example, using image segmentation models to assist in heart muscle surgery. However, such models are often black boxes, meaning it is difficult to know the key factors behind their decisions. Therefore, explainability techniques like Grad-CAM, which generate 2D attention maps to explain AI decisions, are especially important. However, most current Grad-CAM methods can only produce 2D attention maps, making it difficult to provide spatial explanations for 3D models. Therefore, this study proposes an interactive visualization framework that combines Grad-CAM and volume rendering, applied to the 3D image segmentation model, NIfTI. It not only helps users such as medical professionals understand the basis of the model's decisions, but also assists developers in adjusting and optimizing the model's architecture. The main contributions of this study are as follows. Firstly, it is the first to apply Grad-CAM to the medical image segmentation model NIfTI. Secondarily, it combines Grad-CAM and volume rendering techniques, allowing users to freely and instantly view Grad-CAM generated attention maps from multiple perspectives. Thirdly, this study provides layer-wise and channel-wise visualization features, enabling users to understand the model's internal mechanisms and the distribution of semantic features. The NIfTI model explained in this study was proposed in 2023. It is primarily used for segmenting cardiac muscle in CT images. The reasons for choosing Grad-CAM are as follows. Firstly, Grad-CAM generates intuitive attention maps focused on a single class. Secondarily, it does not require any modification to the original model architecture. Thirdly, Grad-CAM is already widely used in medical imaging, providing strong technical and theoretical support. Grad-CAM is an explainability technique suited for interpreting 2D image classification models. The SegXResCAM method proposed in 2023 has been effectively applied to explain 2D image segmentation models. In 2023, a team from Madras University successfully extended Grad-CAM to 3D image classification tasks, applying it to lung cancer CT classification. In 2025, a research team from Cochin University of Science and Technology applied Grad-CAM to the 3D UNET model for 3D image segmentation, but their results were blurry 2D attention maps. In contrast, the method proposed in this study presents clear Grad-CAM attention maps directly in 3D, allowing users to observe the model's key decision areas in real time from multiple angles. This provides more intuitive explainability, especially for 3D structures like the cardiac muscle. Next, the overall system design will be introduced. The system consists of 3 core modules. Grad-CAM Computation and Data Preprocessing Module, responsible for performing Grad-CAM calculations and generating attention map tensors. 3D Volume Rendering Module, responsible for rendering the generated attention map tensors into 3D images. Integration Module, responsible for combining the 2 modules above and incorporating the graphical user interface. The reason for separating Grad-CAM computation and volume rendering into 2 independent modules is that Grad-CAM calculation mainly relies on deep learning frameworks such as PyTorch and MONAI, while volume rendering depends on VTK for real-time rendering. Since both heavily use the GPU, separating them helps prevent resource conflicts. In the Grad-CAM Computation and Data Preprocessing module, data preprocessing is performed first. First, the images are resampled to a uniform voxel spacing. Next, the entire image is divided into 4 blocks of 128 by 128 by 128 voxels for model inference. Next comes the Grad-CAM calculation. To explain the 3D image segmentation model NIfTI, this study does not use global average pooling to compute weights. Instead, it adopts voxel-wise weighting. In the volume rendering module, this study uses raycasting, a method of volume rendering, to perform the rendering. On the left are the camera and the image screen, where each pixel emits a ray that passes through the 3D volume data. The rays sample points along their paths inside the volume, which are then converted into colors and opacity using transfer functions. These sampled values are enhanced with lighting effects based on the ray direction, and finally accumulated from front to back to determine the final color of each pixel in the rendered image on the left. Finally, integration is performed in the integration module. The rotating image on the right is the result rendered by the volume rendering module. This study enables dynamic adjustment of color and opacity through transfer function modifications and supports rendering attention maps either independently or overlaid with the original CT images. It also offers the ability to adjust the rotation speed of the images. It also includes layer selection and channel selection features. Additionally, it provides screenshot and record video functions. Now we showcase our implementation through two applications. The first demonstrates how to interpret the UNet-CNX model. Using layer-wise visualization, users can observe how attention regions shift across layers during inference, offering intuitive insights into the model's segmentation behavior. Furthermore, channel-wise visualization allows observation of attention maps for different channels within the same layer. The second application is using the system to explain the segmentation results of UNet-CNX. For example, during manual annotation of cardiac muscle, UNet-CNX is first used for initial segmentation, followed by manual refinement in the 3D slicer software. In this process, any questions or doubts about the UNet-CNX segmentation results can be reasonably explained using this system. For example, the segmentation results for the left atrial appendage and the superior vena cava are poor. According to the attention maps provided by this system, the UNet-CNX model shows very low confidence that these two areas are cardiac muscle during inference. The segmentation results for the left ventricle and right atrial appendage are very accurate. According to the attention maps provided by this system, the UNet-CNX model is highly confident that these two regions are cardiac muscle during inference, as the attention maps are fully red and completely opaque. UNet-CNX shows consistent strengths and weaknesses across segmentation of 40 Hz. This system provides reasonable explanations for these observations. The contribution of this system lies in being the first to apply Grad-CAM to a 3D image segmentation model for cardiac muscle, combined with volume rendering to generate 3D attention maps. This system separates Grad-CAM computation and rendering, simplifies the design and inference of the UNet-CNX model, and uses voxel-wise weighting to better explain 3D image segmentation models. Finally, it provides layer-wise and channel-wise visualization features.